There is a moment, just before the sun fully clears the horizon, when the Badlands hold their breath. The light arrives slowly, the way it always does in open country, not all at once, but in gradual degrees, feeling its way across the tops of the ridges before it reaches the lower places. The highest formations catch it first. They glow briefly in shades of pale amber and dusty rose, colors that belong more to early morning than to any hour that follows. The shadows between the ridges are still long and blue. The canyons below are still cool. A thin wind moves across the grass at the edge of the formations, bending the dry stems in one direction, then releasing them, then bending them again. There is no other sound. You could stand at the edge of one of the overlooks in the South Dakota Badlands and listen for a long time without hearing anything made by a human hand. The interstate is far enough away that it disappears entirely. The visitor center, the parking areas, the interpretive signs, all of it belongs to a different world. Here, at the rim of the formations, there is only the wind and the light and the landscape spreading outward in every direction until it meets the sky. If you find this kind of journey worthwhile, please consider subscribing to History's Sleepy Time. It helps more than you might expect, and it means we can keep making these long, quiet documentaries together. At first, the Badlands seem to offer very little. The formations are dramatic. Anyone who has ever seen them understands that immediately, but dramatic in a way that feels almost inhospitable. There are no obvious rivers. There is very little shade. The vegetation is sparse, consisting mostly of short grasses, drought-resistant shrubs, and the occasional yucca plant standing alone against a ridge. The soil, where it exists at all, is pale and thin. The rock itself, the exposed walls of sediment that give the Badlands their particular character, is soft in many places, easily crumbled between the fingers, deeply layered in bands of gray and cream and pale tan and burnt orange. The whole landscape looks as though something has been peeling it away for a very long time. That impression is not wrong. Something has been peeling it away. It has been doing so for millions of years, and it has not finished. If you are new to this landscape, the Badlands can seem at first like a place where very little has happened, where nothing grows easily, where the wind erodes rather than nourishes, where the earth beneath your feet seems to resist the idea of life in any form. The formations rise in shapes that do not correspond to anything familiar. Stepped walls and pointed spires and long flat ridges with deeply notched sides, narrow gullies cutting between formations that look as though they were assembled from layers of compressed powder rather than solid stone. The whole terrain seems to belong to some older logic, some arrangement of forces that operated before the current world was established. And in fact, it does. The Badlands are not empty. They have never been empty. What lies within those walls, within every exposed layer of sediment, within every eroded gully and crumbling ridge, is a record of time so vast that even the most patient human mind can only begin to approach it. The formations we see today, the ones lit by this particular early morning light, are the product of processes that began long before any human being walked this continent. They preserve within their layered walls evidence of landscapes that have been completely erased from the surface of the earth. Landscapes that were wet where this place is now dry, forested where this place is now open, and filled with animals that no living person has ever seen. The Badlands look like an ending. In certain ways, they are an ending, the slow, continuous ending of rock that was once buried far below the surface, gradually brought to light through millions of years of erosion. But they are also a record. A deep, improbable, quietly extraordinary record of everything that came before. If you know how to read it, those layered walls have a great deal to say. This documentary is an attempt to listen. And if you are settling in for a long, quiet evening or finding your way towards sleep, we are glad you are here. Take a slow breath. The Badlands have been waiting a very long time. There is no reason to hurry. Now, let us begin at the beginning, or rather, let us begin where we are always forced to begin, which is at the surface. The Badlands of South Dakota occupy a region of the Great Plains that has been shaped, over millions of years, into one of the most visually distinctive landscapes in North America. The formations lie roughly in the southwestern part of South Dakota. Within and around Badlands National Park, a protected area of more than 200,000 acres that preserves not only the geological formations themselves, but the mixed grass prairie that surrounds them, the wildlife that inhabits both environments, and the extraordinary fossil record contained within the rock. The term Badlands is not unique to South Dakota. It describes, more broadly, a type of terrain characterized by steep ridges, narrow gullies, and sparse vegetation. Terrain that forms when soft sedimentary rock is exposed to erosion by water and wind over long periods of time. Similar landscapes exist in other parts of North America and around the world, but the South Dakota Badlands have become, for many people, the defining example of this kind of terrain. They are large enough to feel genuinely remote. They are exposed enough to reveal the geology in remarkable detail. And they contain a fossil record that has drawn scientists from around the world for nearly 2 centuries. The Lakota people, who have lived on and near these lands for generations, have their own name for this landscape. The Lakota word, Mako Sika, translates roughly as bad land or land that is difficult to travel through, and it captures something essential about the terrain, not that it is without value, but that it presents a particular kind of challenge to anyone moving through it on foot. The formations create an irregular surface of ridges and gullies that can be disorienting, especially when the light is flat or when the dry washes and eroded channels all begin to look the same. The landscape does not offer easy navigation. It does not invite casual passage. The Lakota relationship with this landscape extends much further back than the era of Euro-American exploration. The Great Plains, including the region that is now Badlands National Park, was home to the Lakota and their ancestors for centuries before European contact. And the knowledge of this terrain, its sources of water, its seasonal patterns, its useful plants, its animal populations, represented generations of accumulated understanding. The fossil bones that eroded out of the formations were not invisible to indigenous peoples who traveled through or lived near this land. Lakota oral tradition includes references to the large bones found in the earth, which was sometimes understood in the context of older stories about the world's past, stories that reflected a long cultural engagement with a landscape that was clearly, even to careful human observers, doing something unusual. What that unusual thing was, and why the landscape looks the way it does, is a question that requires us to think about time in a way that does not come naturally to most of us. Human beings are reasonably good at thinking about decades. We can imagine the span of a human life with some accuracy. We can hold in our minds the distance between, say, the founding of the United States and the present day, roughly 2.5 centuries, a period that feels both distant and tangible, populated with people whose names we recognize and events whose consequences we can still observe. We can push further back, if we try, to the medieval period, to classical antiquity, to the very early civilizations of the ancient world. These distances are harder to feel, but we can manage them with some effort. But the formations we are looking at in the Badlands were not shaped by anything that happened within the last 10,000 years, or the last 100,000 years, or even the last 1,000,000 years. The sediments that make up the Badlands began accumulating somewhere between 23 and 34 million years ago, during a period of Earth's history so remote from our own that the animals living on this continent at that time would be unrecognizable to a modern observer. The erosion that has been steadily reducing those formations has been underway for roughly 500,000 years, a period that is itself longer than the existence of our own species, Homo sapiens. To understand the Badlands, we have to learn to think in a different kind of time. Not human time, not even civilizational time, something much older than either. Geologists use the term deep time to describe this kind of temporal scale. The phrase was popularized in the 20th century, though the concept had been developing in scientific thought since at least the 18th century, when geologists first began to recognize that the Earth's rock record demanded a timescale far beyond anything that human tradition had previously imagined. Deep time is not simply a matter of large numbers. It is a genuine shift in perspective. It requires recognizing that the world we inhabit is not the world that has always existed, that landscapes come and go, that climates shift, that oceans advance and retreat, that mountains rise and are then gradually worn down, that species appear and disappear, and that all of this happens on a timescale that makes human civilization seem like the briefest of afterthoughts. The Badlands are one of the places on Earth where deep time is not merely a concept. It is visible, you can see it in the walls. Each layer of sediment represents a different period of deposition, a different environment, a different climate, a different set of conditions that existed on this part of the continent at a specific moment in geological history. The bands of different color that run horizontally across the formations are not random. They are a record. Each one was laid down under specific conditions that left their signature in the chemistry and texture of the sediment. Darker bands may reflect periods of greater organic material or different moisture. Paler layers may indicate volcanic ash falls or periods of different drainage. The thick gray units, the buff-colored muds, the streaks of orange and lavender, each represent something that was happening here or nearby during a particular span of time. Reading those layers is not a simple matter. It requires the tools and training of geology and paleontology, but even without that training, there is something in the visual experience of those layered walls that communicates the idea, if not the precise content, of what they contain. They look like a record. They look like pages. And in a very real sense, that is exactly what they are. The formations that we can see in the Badlands are only the visible portion of a much larger geological story. What lies beneath the surface, beneath the eroded ridges and gullies and exposed canyon walls, is a continuation of the same record, extending downward through layers of rock that have not yet been reached by the processes of erosion working at the surface. And what lies within those layers, both above and below the current surface, is a fossil record of extraordinary richness. The word fossil comes from the Latin fossilis, meaning something dug up from the earth. The original usage was broader than our modern one. It referred to anything found by digging, including minerals and crystals that we would not today classify as fossils at all. Over time, the word narrowed to its current meaning, the preserved remains or traces of organisms that lived in the geological past. A fossil may be a bone, a shell, a tooth, a piece of petrified wood, a footprint, a burrow, or any other evidence of a living thing that was somehow preserved within the rock record. Fossilization is a rare process. The overwhelming majority of organisms that have ever lived on Earth left no fossil record at all. When an animal dies in the open, its body is quickly discovered by scavengers and decomposers. Bones that are not quickly buried are exposed to weathering, which breaks them down into smaller and smaller fragments until nothing recognizable remains. The conditions required for fossilization are quite specific. The organism or parts of it must be buried quickly enough to be protected from complete decomposition. And the burial must take place in a geological environment where the sediment will eventually become rock rather than simply being reworked and scattered by subsequent water or wind. In environments where rivers regularly deposit fine-grained sediment, ancient floodplains, the margins of rivers and lakes, the floors of shallow bodies of water, the conditions for fossilization are somewhat more favorable. Bones or shells that sink into soft mud may be covered quickly enough to avoid complete destruction. Over long periods, the sediment above compacts under its own weight and gradually transforms into rock, and the organic material of the buried organism may be slowly replaced by minerals drawn from the surrounding rock. What remains after this process has run its course over thousands or millions of years is a mineralized replacement of the original structure, harder than bone, heavier, often still retaining the fine details of the original anatomy. This process is not instant. Between the moment an animal dies and the moment its fossilized remains are exposed at the surface of a formation like the Badlands, millions of years may pass. The animal lived its life in a world that no longer exists. It died, was buried, was gradually compressed and mineralized within the rock, remained hidden within that rock for an almost unimaginable span of time, and then, as erosion slowly removed the material above it, began to approach the surface once again. When a fossil finally appears at the surface of a Badlands formation, it does so because the rock that once covered it has been removed. Rain and wind have slowly worn away the sediment above, working downward layer by layer over thousands of years, until finally a fragment of bone or tooth or shell appears at the edge of an eroded wall. At that moment, something that has been hidden for tens of millions of years is, for the first time since it was buried, exposed to the open air. That moment of exposure is both a revelation and a countdown. Because the same forces of erosion that brought the fossil to the surface will, if left unchecked, continue to work on it. Exposed to rain, freeze-thaw cycles, and the abrasion of wind-blown sediment, a fossil that has survived tens of millions of years within the rock may be destroyed within decades once it reaches the surface. The Badlands are simultaneously revealing their fossil record and erasing it. New fossils are exposed every year by ongoing erosion. Old fossils, inadequately protected or simply undiscovered before erosion claims them, are lost. This is one of the quiet paradoxes of the Badlands. The landscape reveals its history by slowly destroying it. For paleontologists, scientists who study the fossil record to understand the history of life on Earth, the Badlands represent one of the most important fossil localities in North America. The combination of abundant fine-grained sediment from the relevant geological periods, extensive erosion that continuously exposes new material, and a landscape that allows for systematic survey across large areas has made this region a crucial source of information about the animals and environments of a specific period in Earth's history. The fossils found here have changed scientific understanding of how certain groups of mammals evolved, how ecosystems responded to environmental change, and what the North American continent looked like during a period that preceded our own by tens of millions of years. The question the Badlands asks of anyone who looks at it carefully is this: what kind of world produced these layers? What was this place before erosion reduced it to these pale, soft, beautiful ridges? What animals walked across it? What rivers moved through it? What did the sky look like, and what grew beneath it? Those are the questions that have drawn scientists to the Badlands for generations. They are the questions that the fossil record, imperfect and incomplete as it always is, continues to answer slowly, carefully, one fragment at a time. To understand how the Badlands came to look the way they do today, it is necessary to go back further than the fossils themselves, further back than the ancient environment that produced them, to a period when none of this terrain yet existed, and when the forces that would eventually shape it were only beginning to move into position. The story of the Badlands Formation begins with a much older landscape, one that lies beneath the fossil-bearing sediments as a kind of geological foundation. Beneath the Badlands formations, there is a layer of ancient crystalline rock, granite and related materials that was once part of the deeper fabric of the continent. Above that, there are older sedimentary layers that were deposited during earlier geological periods, including a thick layer of Pierce shale, dark marine shale, that was laid down at the bottom of a vast inland sea that once covered much of the interior of North America during the Cretaceous period, roughly 66 to 100 million years ago. The Western Interior Seaway, as this ancient ocean is known, was a remarkable feature of North America's geological past. At its greatest extent, it divided the continent into two separate landmasses, the western region, known as Laramidia, and the eastern region, known as Appalachia. The seaway was relatively shallow by ocean standards, but broad, stretching from what is now the Gulf of Mexico northward through the Great Plains and into what is now the Arctic. The sediments deposited in this sea, fine muds and silts, accumulated over millions of years, eventually forming the thick sequences of dark shale that underlie the modern landscape across much of the Great Plains. When the Cretaceous period ended and the seaway gradually retreated, the continental interior that had been submerged beneath it was exposed once again. The landscape that emerged was low and flat, a broad plain drained by rivers flowing generally eastward from the rising mountains to the west. Those mountains, the ancestral Rocky Mountains, which were uplifting during this period as a result of tectonic forces operating along the western margin of the continent, were shedding enormous quantities of sediment into the streams and rivers that drain their eastern slopes. That sediment was being carried eastward and deposited across the plains in thick sheets of sand, silt, and mud. The sediments that form the most fossil-rich layers of the Badlands were deposited during this period, specifically during the Eocene and Oligocene epochs, which together span roughly from 56 million years ago to approximately 23 million years ago. The particular formations most associated with the Badlands fossil record are the Chadron Formation, which dates to the late Eocene, roughly 37 to 34 million years ago, and the Brule Formation, which dates to the Oligocene, roughly 34 to 30 million years ago. These two formations make up the bulk of what we see when we look at the Badlands today. The Chadron Formation is the older of the two. It consists primarily of dark gray mudstones and siltstones, reflecting a depositional environment that scientists believe was characterized by broad, low-gradient river systems with meandering channels, adjacent floodplains, and areas of wetland or shallow, standing water. The climate during the late Eocene was warmer and more humid than the climate of today's Badlands. The vegetation was more substantial. The landscape supported a greater variety of animals, many of which are now known only from the fossil record. Above the Chadron Formation lies the Brule Formation, lighter in color, often appearing in shades of buff, tan, and pale gray, sometimes streaked with pink or lavender. The Brule was deposited under conditions that appear to have been somewhat drier than those of the Chadron. Still, a river-dominated landscape, but one that may have experienced more pronounced seasonal variation in rainfall. and one that was gradually shifting toward a more open environment as the Eocene gave way to the Oligocene. Throughout both formations, there are thin but distinctive layers of volcanic ash. These layers, sometimes appearing as bright white or pale gray bands within the otherwise muted rock, are the preserved remnants of eruptions that occurred far to the west, in what is now Wyoming and Idaho, during a period of significant volcanic activity in the Rocky Mountain region. The ash drifted eastward on atmospheric currents and settled across the landscape, eventually becoming incorporated into the sediment being deposited by the rivers. Today, these ash layers are extremely useful to geologists and paleontologists because they can often be chemically analyzed and dated with considerable precision, providing reliable age markers within the otherwise difficult-to-date sedimentary sequence. One of the most important of these ash layers in the Badlands is a deposit sometimes called the Rockyford Ash, which helps define the boundary between the Chadron and Brule formations and provides a reliable chronological marker within the overall sequence. The presence of these datable ash layers is one reason the Badlands fossil record can be connected to a broader geological timeline with some confidence. Running through both formations are the traces of ancient rivers and streams, channels cut into older sediment and filled with coarser material, lenses of sand that represent the deposits of ancient river bars, and the fine-grained overbank deposits that accumulated on the floodplains between flooding events. These features, visible in some places as subtle changes in color or texture within the exposed walls, allow geologists to reconstruct the general pattern of ancient drainage across the landscape, to trace in broad outline where the rivers ran, how wide they were, and how frequently the surrounding floodplains were inundated. After the sediments were deposited, the landscape underwent a different kind of change. The region experienced gradual uplift as a result of tectonic processes, rising slowly over millions of years until the rivers that once deposited sediment across the plain began instead to cut downward into it. The shift from deposition to erosion marked the beginning of the long process that has been sculpting the Badlands ever since. Erosion in the Badlands is driven primarily by water. Despite the region's relatively dry climate, which today receives only moderate annual precipitation, even modest rainfall has a significant effect on the soft sedimentary rock. The formations are composed largely of consolidated, but not extremely hard mudstone and siltstone, materials that absorb water easily and are vulnerable to being carried away when wet. During rain events, water sheets off the nearly unvegetated surfaces of the formations in thin films, carrying fine particles of sediment with it. Gullies form, deepen, and extend backward into the hillside through a process called headward erosion. Over thousands of years, these gullies coalesce and deepen into canyons, and the canyon walls retreat, reducing the width of the ridges between them. Wind plays a secondary but not insignificant role. The particles that water dislodges and deposits in the lower reaches of the formations are subsequently picked up by wind and carried away from the landscape entirely, preventing the accumulation of sediment that would otherwise slow the erosion process. The net effect is a steady and ongoing removal of material from the surface, a removal that continues today, and that is estimated to be lowering the general surface of the Badlands formations by roughly an inch per year in some areas. That rate may sound slow. Over a human lifetime, it amounts to only about 6 or 7 feet of material, but over thousands of years, it represents a substantial transformation of the landscape. The formations we see today are not the formations that existed even a relatively short time ago in geological terms. The landscape is in motion, slow, continuous, and patient motion, but motion nonetheless. This ongoing erosion is what makes the Badlands one of the most productive fossil localities in North America. As the surface is lowered, fossils that were once buried deeply within the rock approach the surface. When they finally emerge, when the last few inches of overlying sediment are removed by rain or wind, they appear at the surface of the formation, sometimes protruding slightly from the rock face, sometimes lying loose at the base of an eroded slope. Paleontologists who survey the Badlands are, in a very real sense, waiting for the landscape to deliver its contents. Each year, erosion removes another fraction of an inch of rock and reveals whatever lay hidden beneath it. The landscape is, in this sense, constantly in the process of reading itself aloud. The formations are like a book being read by the weather, page by page, layer by layer, at a pace that no individual human life is long enough to witness in any meaningful depth. But science has given us the tools to read along, and what those tools have revealed about the ancient world hidden within the Badlands is worth a great deal of careful attention. There is a particular quality of light in the Badlands in the hour before sunset. The low angle of the sun catches the horizontal banding of the formations in a way that makes each layer distinct, not just visually different, but almost individually present, as though each band of sediment were asserting its own identity against the others. The grey mudstones of the lower formations look heavier in that light, more compressed. The paler buff-colored layers of the upper formations seem almost to glow. The thin streaks of volcanic ash, where they are exposed, appear almost white against the surrounding material, faint lines drawn across the canyon walls with a precision that no human hand could replicate. These layers are the pages of the archive. Each one was deposited under a specific set of conditions, during a specific window of geological time, and each one preserves within it, in varying degrees of completeness, a record of what was happening in this part of the world during that window. Reading them is not a matter of simply looking. It requires a trained understanding of what different types of sediment indicate, what the presence or absence of certain minerals suggests about past conditions, and how the sequence of layers relates to the broader geological timeline that has been constructed from thousands of sites across the continent and around the world. Geologists who study sedimentary sequences use the term stratigraphy to describe the systematic analysis of layered rock. The foundational principle of stratigraphy, known as the law of superposition, is straightforward. In an undisturbed sequence of sedimentary layers, the oldest layers are at the bottom and the youngest are at the top. This seems obvious once stated, but its implications are profound. It means that by moving upward through a sequence of rock layers, you are moving forward through time, and conversely, by moving downward, you are moving backward. The Badlands formations, read from bottom to top, represent a journey forward through roughly 10 to 15 million years of geological history. The base of the Badlands sequence, the Chadron Formation, contains material dating to the late Eocene epoch, a period that ended approximately 33 to 34 million years ago. The Eocene itself was a remarkable interval in Earth's history. It followed a period of significant warming that occurred at the beginning of the Eocene, roughly 56 million years ago, an event known as the Paleocene-Eocene thermal maximum, during which global temperatures rose sharply and remained elevated for tens of thousands of years. By the late Eocene, the climate had begun to cool somewhat from those extreme temperatures, but the world was still considerably warmer than today. Forests extended further toward the poles. Sea levels were different. The distribution of land and sea was recognizably similar to today's, but not identical. Significant geological changes were still underway on every continent. In what is now the northern Great Plains, the late Eocene environment was shaped primarily by the drainage systems flowing eastward from the ancestral Rocky Mountains. Rivers deposited sediment across broad, low-lying plains. Floodplains extended on either side of the main channels, inundated periodically during high water and covered with vegetation during drier periods. The climate appears to have been warmer and more humid than the modern Badlands, more seasonal than a tropical environment, perhaps, but significantly wetter and more vegetated than the dry, semi-arid landscape we see today. Evidence for this interpretation comes partly from the fossils themselves. The types of animals and plants preserved in the Chadron Formation indicate an environment capable of supporting a more diverse and water-dependent fauna than the modern Great Plains supports, and partly from the sediment itself, which contains features that geologists associate with waterlogged or seasonally flooded soils. Above the Chadron Formation, the Brule Formation represents a somewhat later period, the Oligocene epoch, which began approximately 33 to 34 million years ago and continued until about 23 million years ago. The Oligocene was, globally, a period of continuing climate cooling. The Antarctic ice sheet began to develop during the early Oligocene, drawing water out of the ocean and contributing to a drop in global sea levels. The cooling affected vegetation patterns worldwide, contributing to the expansion of more open, grass-dominated habitats at the expense of forests, a trend that would continue and intensify in the Miocene epoch that followed. In the Badlands, the Brule Formation reflects this general trend toward cooler and drier conditions. The sediments suggest a somewhat more open landscape, still a river-influenced environment, but one that may have had more extensive grassland or open woodland areas than the Chadron landscape below. The fauna preserved in the Brule is different from that of the Chadron in ways that are consistent with this environmental shift, though many animal groups span both formations and represent the continuity of lineages across the Eocene-Oligocene transition. Understanding the transition between these two formations, understanding what changed, why it changed, and what the consequences were for the animals and ecosystems of this region, is one of the central research questions that has drawn paleontologists to the Badlands for generations. The Eocene-Oligocene boundary is a significant moment in the history of life on Earth, a period of major faunal turnover that saw the extinction of many archaic mammal groups and the diversification of lineages that would go on to dominate the later Cenozoic. The Badlands sit almost perfectly astride that boundary, preserving a record of the world both before and after this transition that is difficult to match anywhere else on the continent. Reading the layers of the Badlands, then, is not simply an exercise in identifying different types of rock. It is an attempt to reconstruct a sequence of worlds, to understand not just what existed here at a given moment, but how the landscape and its inhabitants changed over time in response to forces that were themselves changing. The archive in the walls is not a static record. It is a record of change, slow, continuous, deep-time change, and reading it requires both patience and the willingness to think across timescales that dwarf anything in human experience. Let us try to do something difficult. Let us try to set aside the landscape we can see, the dry ridges, the sparse grass, the pale sediment in the canyon walls, and attempt to reconstruct, as carefully as the evidence allows, the world that once existed here. This is not a simple exercise. Scientific reconstruction of ancient environments is a careful and often slow process, dependent on multiple lines of evidence that must be assembled and interpreted before any meaningful picture can emerge. The fossil record provides direct evidence of the organisms that lived in a particular environment. The sedimentary record provides evidence of the physical conditions, the types of rivers, the nature of the soils, the frequency of flooding, the presence of volcanic ash. Chemical analysis of the sediment can reveal information about past temperatures and rainfall patterns. The specific combination of plant and animal fossils can be used, in conjunction with what we know about the ecological requirements of living relatives, to constrain the range of possible environments in which the ancient community could have existed. With those caveats in place, and with the understanding that what follows is a reconstruction based on evidence, not a direct observation, let us try to walk into the ancient Badlands. The late Eocene landscape that is now preserved in the Chadron Formation was, based on current scientific understanding, a broad and relatively flat plain cut by rivers and streams draining from higher ground to the west. The rivers were not, in most cases, the kind of steep, fast-moving mountain streams that we associate with the modern Rockies. They were mature, low-gradient rivers meandering across their floodplains, depositing sediment on their inner banks, cutting into the outer banks of their curves, and periodically overflowing their banks to flood the surrounding plain. The landscape between the river channels was not empty. It was covered, to varying degrees, with vegetation. The nature of that vegetation is something scientists continue to study and debate. The evidence suggests that the late Eocene landscape of the northern Great Plains was not a closed forest in the style of a modern tropical or temperate rainforest. Nor was it anything like the open shortgrass prairie that characterizes the Great Plains today. It was something in between, a mosaic of more densely wooded areas along the river channels, where water was more reliably available, and more open areas of woodland, shrubland, or savanna on the higher ground between the channels. The specific mix of plant species would have been quite different from anything that exists today in this region. The grasses that now dominate the Great Plains had not yet achieved their modern ecological dominance. True grasslands, in the sense of vast, continuous grass-dominated ecosystems, appear to have become widespread only in the Miocene, considerably later than the Eocene and Oligocene deposits of the Badlands. The plants of the Eocene Badlands included species more closely related to subtropical or warm-temperate groups, reflecting the warmer climate of that period. Water was a more significant presence in this landscape than it is today. The rivers and their floodplains would have supported not just more vegetation, but different animals that depended on water or wet environments in ways that the modern Badlands fauna does not. Evidence from the Chadron Formation includes fossil remains of animals associated with aquatic or semi-aquatic environments, suggesting that ponds, marshes, or seasonally flooded areas were part of the landscape. As we move upward through the formation, as time passes and the Oligocene environment of the Brule Formation gradually replaces the Eocene environment of the Chadron, the landscape appears to shift. The climate was cooling, rainfall patterns were changing. The balance between forested and open environments was shifting toward the latter. The rivers continued to flow, and their floodplain deposits continued to bury and preserve the remains of the animals that lived beside them. But the composition of the animal community was changing, some groups diminishing, others increasing, and some appearing for the first time in the regional record. What would a traveler in this ancient landscape have experienced? The air was warmer than the modern Badlands air, especially in summer. The sky was broad and open, as it is today across the Great Plains, but the light falling on the landscape would have fallen on different colors, the greens and golds of a more heavily vegetated world, rather than the pale grays and tans of exposed sediment. The sounds of moving water, rivers and streams crossing the plain would have been more present than they are in the modern Badlands, where water is a rare and temporary visitor. The smell of the landscape would have been different, more organic, more alive, more complicated. And moving through that landscape would have been animals, many of them, some of them now entirely extinct, known only from the fossil record, some of them ancestral to modern groups, recognizable in broad outline but unfamiliar in their specific proportions and details. A few of them representing lineages that still have living relatives today, though those modern relatives have changed substantially over the intervening millions of years. The animals of the ancient Badlands are the subject we must now turn to, because they are, in many ways, the most direct evidence we have of the world that once existed in this place. Before we can speak meaningfully about the animals themselves, it is worth pausing to consider what it means for a fossil to exist at all, not in the abstract sense we discussed earlier, but in the specific context of the Badlands. When an animal died in the ancient landscape of the Chadron or Brule environment, the most likely outcome was that its body would be completely destroyed. Scavengers would find it. Insects would work through the soft tissues. The bones left on the surface would be exposed to rain and sun and the freeze-thaw cycles of seasonal temperature change. Within years or decades, even the hardest bones would begin to fragment. Within centuries, they would be indistinguishable from the surrounding soil. The animal would leave no trace in the geological record. But occasionally, not often, but occasionally, an animal's remains found their way into a depositional environment where the conditions favored preservation. The body might wash into a river channel and become buried under a deposit of sand and silt. A flood might sweep across the floodplain and bury bones that were already lying on the surface under a thick layer of overbank sediment. A carcass might sink into a muddy pond or marsh and be covered before the bones could be scattered. In each of these cases, the rapid burial, rapid in geological terms, meaning days or weeks rather than years, protected the remains from the surface processes that would otherwise destroy them. Once buried, the remains entered a different environment, one of compression, mineral-rich groundwater, and very slow chemical change. Over thousands of years, the original bone, which is itself a composite of organic collagen and inorganic calcium phosphate mineral, underwent gradual transformation. The organic components decomposed, leaving voids within the mineral framework. Groundwater moving through the surrounding sediment deposited additional minerals within those voids, gradually filling them and changing the composition of what had once been living bone. The result, after millions of years, was a structure that retained the external shape and many of the internal details of the original bone, but was now composed largely of rock, heavier, harder, and far more durable than the original material. This process, called permineralization, is the most common form of fossilization in the Badlands. It preserves the three-dimensional structure of bones and teeth with remarkable fidelity, sometimes down to quite fine internal details that provide important information about the biology of the animal. The quality of preservation varies, depending on the specific conditions under which the burial occurred and the nature of the groundwater that moved through the sediment afterward. Some fossils from the Badlands are beautifully preserved, with fine surface texture intact and three-dimensional structure largely undistorted. Others are fragmentary, distorted by the weight of overlying sediment or chemically altered in ways that make them more difficult to interpret. Teeth are often the best preserved elements. Dental enamel, the hard outer coating of a tooth, is the most minerallically dense tissue in a vertebrate body, and it resists the processes that destroy other materials. In many cases, the teeth of an extinct animal are the first material to be exposed at the surface as erosion removes the overlying rock, and in some cases, they are the only material that survives at all. A great deal of what we know about the mammals of the Eocene and Oligocene, including many species from the Badlands, comes primarily from teeth, supplemented by whatever bone material happened to be preserved along with them. The pattern of fossil discovery in the Badlands is heavily influenced by erosion. As the formations erode, fossils are not distributed evenly across the landscape. They tend to concentrate in specific areas, places where the erosion is actively exposing new material. Where the slope, angle, and rock type favor the gradual emergence of fossils rather than their rapid destruction, and where the conditions at the time of deposition were favorable to fossilization in the first place. Certain horizons within the Chadron and Brule formations are particularly fossil-rich, layers that were deposited in or near ancient river channels or floodplain environments where the burial conditions were consistently favorable. Paleontologists who survey the Badlands have developed a practiced eye for recognizing these productive areas. The color and texture of the sediment, the angle and character of the erosion, the presence of certain minerals or features associated with ancient soils or river deposits. All of these provide clues about where fossil material is most likely to be found. A trained observer walking slowly across the surface of a Badlands slope can identify, from a distance, the shape of a partially exposed bone or the distinctive sheen of fossilized tooth enamel against the duller surface of the surrounding rock. Much of the work of Badlands paleontology is simply this: patient, systematic walking in harsh conditions across terrain that offers no shade and very little water, watching the surface of the rock for something that does not quite belong to the modern world. When a fossil is identified, the next decision is how to proceed. A small, isolated fragment lying loose on the surface may be quickly documented and collected with minimal effort. A larger specimen partially embedded in the rock face requires a different approach, one that involves carefully removing the surrounding sediment to determine the extent of the specimen, assessing the condition of the fossil, and deciding on the safest method of extraction. In many cases, the fossil is jacketed in field plaster, a technique developed in the 19th century and still widely used today, in which the exposed fossil and a layer of surrounding rock are covered with strips of burlap soaked in plaster of Paris, creating a rigid protective case that allows the specimen to be transported safely to a laboratory. In the laboratory, the real work of preparation begins. Under magnification, using fine tools, dental picks, air scribes, brushes, sometimes chemical consolidants, preparators remove the remaining rock matrix from the fossil surface, exposing the specimen as completely as the preservation allows. This process can take weeks or months for a large or delicate specimen. It requires patience, skill, and a detailed understanding of the anatomy of the animal, so that the preparator knows where bone ends and rock begins. What emerges from this process, when it goes well, is a fossil that can be examined, measured, compared, described, and ultimately published as part of the scientific record. Each well-documented fossil adds a data point to the growing picture of ancient life in the Badlands. Each new specimen may confirm something already known, or it may complicate existing interpretations, or occasionally it may represent something entirely new to science. A species previously unknown, a relationship between groups previously unrecognized, or evidence of a behavior or ecological role that had not been suspected. The fossils of the Badlands have been yielding information of exactly this kind for nearly 2 centuries, and the animals they reveal are worth knowing. To understand the fauna of the ancient Badlands, the animals that left their bones in the sediment of the Chadron and Brule formations. It helps to understand something about the broader context of mammalian evolution during the Eocene and Oligocene. The Cenozoic era, the period of geological time that began approximately 66 million years ago with the extinction of the non-avian dinosaurs and continues to the present, is sometimes described informally as the Age of Mammals. This characterization is a simplification, but it captures something real. The extinction event at the end of the Cretaceous period removed the large non-avian dinosaurs from the ecosystems they had dominated for more than 150 million years, and opened ecological space that mammals, which had existed in various forms throughout the Mesozoic, but had largely been small, nocturnal and ecologically subordinate, rapidly moved to fill. By the Eocene, mammals had diversified enormously, occupying roles in ecosystems that ranged from small ground-dwelling insectivores and herbivores to larger browsing animals, semi-aquatic forms, early predators, and tree-dwelling species. Many of the mammals of the Eocene and Oligocene belonged to groups that are now entirely extinct, groups that left no living descendants, and that represent evolutionary experiments, complete in themselves, that simply did not persist into the modern world. Others were the ancestors of living groups, early members of lineages that would eventually give rise to horses, rhinoceroses, deer, pigs, dogs, cats, and many other modern families. Understanding the difference between these categories, between animals that were end points and animals that were beginnings, is one of the intellectual challenges of studying the Badlands fossil record, and it requires the careful comparative work of evolutionary biology and paleontology. Among the most characteristic animals of the late Eocene Badlands was a group known as the Titanothers or Brontotheres. These were large, plant-eating mammals belonging to a group that is now entirely extinct, but that was, during the Eocene, among the most imposing animals in North America. The Brontotheres were distantly related to modern horses and rhinoceroses. All are members of the larger mammalian group called the odd-toed ungulates, but they developed along their own distinct evolutionary path, growing steadily larger over the course of the Eocene and developing elaborate bony projections on their skulls that varied considerably in shape between species, and that may have been used in social display or combat, as similar structures are in living animals today. The largest Brontotheres of the late Eocene were genuinely large animals, comparable in size to a modern rhinoceros, with a heavy, barrel-shaped body, relatively short legs, and the characteristic bony horns or bosses on the snout. Fossils of Brontotheres have been found in the Chadron Formation of the Badlands, providing direct evidence that these animals were part of the fauna of this region during the late Eocene. Their presence tells us something important about the environment. Brontotheres were browsers feeding on leafy vegetation rather than grass, and their abundance in the late Eocene fossil record is consistent with an environment that offered substantial shrubby or low forest vegetation, the kind of habitat that a large browser would require. The Brontotheres did not survive beyond the Eocene. They appear in the fossil record through the late Eocene and then disappear entirely, their extinction coinciding broadly with the major environmental changes that marked the end of the Eocene epoch. Why they went extinct while other groups survived is not entirely certain. The shift toward cooler and drier conditions and the accompanying changes in vegetation may have reduced or eliminated the browsing habitat they depended on. Whatever the cause, the Brontotheres are among the most dramatic examples of a complete extinction, an entire order of mammals that once dominated parts of the Eocene landscape and left no descendants in the modern world. Alongside the Brontotheres in the late Eocene landscape lived a variety of other animals. Primitive rhinoceroses, early members of a group that would go on to diversify substantially in the Oligocene and Miocene, were present in the Badlands fauna. These early rhinos were not necessarily large or horn-bearing in the way that modern rhinoceroses are. Some of the Oligocene representatives in particular were quite different from their modern relatives, including the Hyracodonts, a group of relatively slender-limbed rhinoceroses that may have been capable of moving at speeds greater than a modern rhino, and which are sometimes informally described as running rhinos. There were also early members of the horse lineage present in the Badlands. The ancient horses of the Eocene and Oligocene, genera such as Mesohippus, known from Badlands material, were quite different from the large, single-toed, long-legged animals we know today. They were small, roughly the size of a large dog, with 3 toes on each foot rather than 1, and with teeth adapted for browsing on soft vegetation rather than the high-crowned, grinding teeth of modern horses, which are adapted for processing the tough, silica-rich grasses that became dominant in the Miocene. The evolution of the horse family across the Cenozoic is one of the most thoroughly documented cases of evolutionary change in the fossil record. And the Badlands specimens contribute importantly to that record, showing a stage of horse evolution that was transitional between the earliest known horse ancestors and the more derived horses of the later Cenozoic. Among the more unusual inhabitants of the ancient Badlands was a group of animals known as Oreodons. The Oreodons, whose name means something like mountain teeth, were a group of medium-sized plant-eating mammals that is, intriguingly, entirely without close modern relatives. They belonged to a broader group that includes modern pigs, hippos, and ruminants, but Oreodons themselves represent a distinct and now completely extinct branch of that group. They were extremely abundant in the Badlands during the Oligocene. Odont fossils are among the most commonly found vertebrate remains in the Brule Formation. So common, in fact, that early collectors sometimes encountered them in extraordinary numbers, with multiple individuals preserved together in what appear to have been mass mortality events, possibly related to drought or flooding. The abundance of Oreodont fossils has made them important reference points in the stratigraphic analysis of the Badlands, since different species appear to characterize different time intervals within the formation, providing a biological clock that can be used to correlate fossiliferous layers across different localities. They were apparently animals that lived in herds or social groups, feeding on the vegetation of the floodplains and river margins, and that were vulnerable, in their abundance, to the same catastrophic events that left their remains preserved in such quantities. Predators were also part of this ancient ecosystem, though they are generally rarer in the fossil record than the plant-eating animals they hunted, a reflection of the ecological reality that predators are always less numerous than prey. The Badlands have yielded fossil material from a variety of carnivores and omnivores of the Eocene and Oligocene, including early members of the dog family animals, belonging to a now extinct group called the Nimrovids, which superficially resembled cats and occupied similar ecological roles, and a variety of smaller carnivorous or omnivorous mammals, whose exact dietary preferences and ecological roles are not always easy to reconstruct. The Nimrovids deserve particular attention because they represent one of the more striking examples of what evolutionary biologists call convergent evolution, the independent development of similar features in unrelated lineages in response to similar ecological pressures. The Nimrovids were not true cats. They belonged to a separate evolutionary lineage that has no modern descendants. But they developed, independently of the true cat family, an elongated upper canine tooth that in some species reached impressive proportions, a feature that the true saber-toothed cats would later independently evolve in a different lineage millions of years later. The nimravids of the Badlands were, in a sense, an earlier experiment in the ecology of ambush predation. Large, relatively powerful carnivores with specialized teeth for killing large prey, operating in an ecosystem that provided them with ample hunting opportunities. What the presence of these predators tells us about the ancient Badlands is as important as what the herbivores tell us. A functioning predator guild of this kind requires not just prey animals, but prey animals in sufficient numbers to support a population of predators year-round. It requires an ecosystem that is productive enough and stable enough across seasons to maintain both the plants that feed the browsers and the browsers that feed the carnivores. The ancient Badlands ecosystem was not a simple or impoverished one. It was a full, complex, functioning community of organisms, a world unto itself, operating according to ecological relationships that may not have a precise modern analog, but that followed the same fundamental principles of energy flow and species interaction that govern all ecosystems. That world is gone now. The animals that lived in it are extinct or transformed beyond easy recognition. The landscape that supported them has been fundamentally altered by millions of years of geological change. The only reason we know it existed at all is because some of those animals, a small fraction, a random sample, an imperfect archive, were buried in the right places at the right times, and the sediment that covered them became the rock that now makes up the walls of the Badlands formations. Those walls, patiently eroding in the wind and rain, continue to give back what was entrusted to them so long ago. The fossils of the Badlands did not wait for science to find them. They had been eroding out of the formations for thousands of years before any trained naturalist or paleontologist arrived in this part of the continent. The evidence was always there, visible at the surface of the formations wherever erosion had done its work. Bones and teeth of unusual size and shape, half embedded in the pale sediment of a canyon wall or lying loose at the base of an eroded slope after a season of rain. Anyone who traveled through this landscape with open eyes would eventually encounter them. The Dakota people and their ancestors, who moved through and lived near this landscape for centuries, were not unaware of the large bones that the formations produced. The Dakota have long held knowledge of this land, its seasonal patterns, its water sources, its dangers, and its unusual features. The fossil bones that emerged from the Badlands cliffs were noted, though their interpretation within Dakota cultural understanding differed fundamentally from the later scientific interpretation that would emerge in the 19th century. Some scholars have noted that certain large fossilized bones may have been associated in various indigenous traditions of the plains with stories about great creatures or beings from an earlier world. Though it is important to be careful here because specific oral traditions vary significantly between nations and communities, and no single unified indigenous interpretation of Badlands fossils can be accurately stated. What can be said with confidence is that the landscape and its unusual contents were known to the people who lived closest to it, long before Euro-American exploration of the region began. The formal introduction of Badlands fossils to Euro-American scientific awareness came in the early 19th century, in the context of the broader American exploration of the West that followed the Louisiana Purchase of 1803. The Lewis and Clark expedition of 1804 to 1806 passed through the general region of the upper Missouri River and northern Great Plains, and while that expedition did not extensively document the Badlands formations directly, it contributed to to a growing Euro-American awareness of the remarkable landscape of the interior West and the unusual natural features it contained. One of the earliest documented references to Badlands fossil material in a scientific context came from fur traders and travelers who moved through the region in the early decades of the 19th century. The fur trade that drove much of Euro-American penetration into the northern Great Plains in this period brought trappers, traders, and their indigenous partners into areas of the landscape that were far from any established Euro-American settlement. Some of these individuals encountered the Badlands formations and the fossil material eroding from them, and accounts of unusual bones in the cliffs of the upper White River region began to filter back to scientific circles in the East. It was physician and naturalist Hiram Prout who, in 1846, published one of the earliest scientific descriptions of a Badlands fossil, a fragment of jaw with teeth that he identified as belonging to a large, unknown mammal. The specimen had been collected from the White River Badlands region and sent to Prout for examination. His description, published in the American Journal of Science, was brief and imperfect by later standards, but it marked the formal beginning of the scientific documentation of the Badlands fossil fauna. The following year, Joseph Leidy, one of the most important American naturalists of the 19th century, began to receive fossil material from the Badlands and to describe it systematically. Leidy, who was based at the Academy of Natural Sciences in Philadelphia and later at the University of Pennsylvania, had a remarkable ability to work rapidly and accurately with fossil material, even when that material was fragmentary. Over the following decades, he described a large number of new species from the Badlands, establishing the basic framework of the White River fauna. As the fossil assemblage of the Badlands and related formations across the Great Plains came to be known, that subsequent researchers would build upon. Leidy's work was accomplished largely from specimens sent to him by collectors and travelers in the field. The logistics of working in the Badlands in the mid-19th century were genuinely formidable. The region was remote, water was scarce, the terrain was difficult, the climate was extreme, and the political situation was complicated by the ongoing conflicts between the United States government and the Dakota and other Plains nations over the lands that the government was progressively seizing or seeking to control. Scientific expeditions into the Badlands during this period operated within a broader historical context of dispossession and violence that is inseparable from the history of the American West. The period following the American Civil War saw an acceleration of both Western exploration and paleontological activity in the Badlands and the broader Great Plains region. This era, sometimes called the Bone Wars in popular accounts, though that term specifically refers to the intense personal rivalry between paleontologists Othniel Charles Marsh and Edward Drinker Cope, was characterized by an extraordinary expansion in the collection of fossil vertebrate material from Western formations. Both Marsh and Cope sent collectors to the White River Badlands, and the competition between their respective expeditions contributed to a rapid increase in the number of species described and specimens collected from the region. Othniel Charles Marsh, who held a professorship at Yale University and directed the paleontological surveys conducted under the authority of the U.S. Geological Survey, organized systematic collecting expeditions to the Badlands and related formations in the 1870s and 1880s. His collectors worked across the White River exposures in South Dakota and Nebraska, shipping large quantities of fossil material back to Yale's Peabody Museum of Natural History. Edward Drinker Cope, who was based in Philadelphia and worked with considerable personal energy and financial investment, also collected extensively from the region during the same period. The specimens accumulated by both men contributed enormously to the scientific understanding of the White River fauna, even as the personal and professional relationship between the two paleontologists descended into a bitter dispute that did neither man credit. The collecting methods of this era were, by modern standards, often crude. Large quantities of fossil material were excavated rapidly, with relatively little attention to documenting the precise location and orientation of specimens within the rock, or the relationship between different specimens found in close association. Much of what was collected was fragmented during extraction or shipping, and arrived at Eastern museums in a condition that required extensive reconstruction before it could be studied. The competitive pressure to describe new species quickly also led, in some cases, to the naming of species on the basis of inadequate material, a problem that subsequent researchers spent considerable effort untangling. Despite these limitations, the work of the 19th century collectors established the Badlands as one of the most important fossil localities in North America, and laid the foundation for a century and a half of subsequent scientific investigation. The collections assembled by Marsh, Cope, Lady, and their contemporaries are still studied today. Many of the species they described, established on the basis of those early collections, remain valid and important components of the scientific understanding of the White River fauna. The 20th century brought a different approach to Badlands paleontology. As the science of paleontology matured and developed more rigorous methodological standards, the emphasis shifted from rapid collection of large numbers of specimens toward more careful, context-sensitive excavation that preserved information about the geological setting of each fossil. The establishment of Badlands National Monument in 1939, later redesignated as Badlands National Park in 1978, provided a formal framework for the management of fossil resources within the most significant part of the formation, requiring that scientific collection be conducted under permit and that specimens be properly documented and deposited in recognized institutions. The South Dakota School of Mines and Technology, now the South Dakota Mines, became an important center for Badlands paleontology in the 20th century, with its Museum of Geology accumulating one of the major collections of White River fauna material in the country. Research programs based at this institution, as well as at universities across the country and at the American Museum of Natural History and other major natural history museums, have continued to add to the scientific understanding of the Badlands fossil record throughout the 20th and into the 21st century. Among the notable finds of the modern era of Badlands paleontology was the discovery of exceptionally well-preserved specimens that allowed scientists to answer questions about anatomy and biology that fragmentary material had previously left unresolved. Careful excavation of articulated or associated skeletons, specimens in which the bones remained in or near their original anatomical positions, rather than being scattered by scavengers or water, provided information about the overall body proportions and posture of animals that had previously been known mainly from teeth and isolated bone fragments. Such specimens are relatively rare in the Badlands, where the conditions of burial and subsequent erosion do not always favor the preservation of complete or undisturbed skeletons, and their discovery represents a significant event in the ongoing reconstruction of the White River fauna. The fossils of the Badlands are not merely evidence of individual species. They are evidence of a functioning ecosystem, a complex community of organisms that existed in a specific environment at a specific time. And when the fossil record of the Badlands is examined not just as a collection of species, but as a sequence of communities changing through time, it reveals something of profound importance, a record of how life on this part of the continent responded to one of the major environmental transitions of the Cenozoic era. The boundary between the Eocene and Oligocene epochs, which is recorded within the Badlands sedimentary sequence at approximately the transition between the Chadron and Brule formations, represents a significant moment in Earth's climate history. Across the globe, the end of the Eocene was marked by a cooling of temperatures and a shift toward drier, more seasonal climates. In Antarctica, the glaciation that would eventually produce the modern Antarctic ice sheet began to develop. Sea levels dropped as water was drawn into the expanding polar ice. Ocean circulation patterns shifted. The distribution of vegetation zones changed across every continent. In the northern Great Plains, these global changes were reflected in the local environment. The warmer, more humid conditions of the late Eocene, conditions that had supported the diverse browsing fauna of the Chadron Formation, gradually gave way to the somewhat cooler and drier conditions of the Oligocene. The vegetation changed, the waterways changed, and the animal community changed with them. Paleontologists who have studied the transition between the Chadron and Brule fauna in the Badlands have documented a pattern of faunal turnover that is complex and still not entirely understood. Some of the characteristic Eocene animals, the Brontotheres, most dramatically disappear from the record entirely at or near the end of the Eocene. Others persist across the boundary and continue into the Oligocene, sometimes with modifications that suggest evolutionary adaptation to the changing conditions. And some groups that are rare or absent in the Chadron become more common and diverse in the Brule, suggesting that the changing environmental conditions favored their expansion. The Oreodons are perhaps the clearest example of Oligocene success. Rare or absent in the late Eocene fauna, they become extremely abundant in the Brule Formation, so abundant, as noted earlier, that their fossils are among the most commonly encountered vertebrate remains in the formation. This abundance may reflect a shift in the vegetation toward types of plant material that Oreodons were well suited to exploit, or it may reflect competitive release following the extinction of the Brontotheres and other large Eocene browsers that had previously occupied some of the same ecological space. The reasons for the Oreodons' Oligocene dominance are not entirely clear, but the pattern itself is well established in the fossil record. The horses of the Badlands also tell an important story about environmental change. The small, three-toed browsers of the Eocene gradually gave way, over the course of the Oligocene and later the Miocene, to larger animals with more complex teeth. Animals that were progressively better adapted for feeding on tougher, more abrasive vegetation. This trend in horse evolution has traditionally been interpreted, at least in part, as a response to the spread of grasslands, ecosystems dominated by grasses with high silica content that would rapidly wear down the simpler, low-crowned teeth of Eocene horses. The Badlands record contributes to this story by documenting the early stages of this transition, showing horse species that were already beginning to shift from the browsing dentition of their ancestors toward the more complex teeth of their descendants. The relationship between the Badlands fossil record and the story of grassland expansion is a particularly interesting one. True grasslands, in the modern sense of vast, continuous ecosystems dominated by grass, appear to have been relatively limited during the Eocene and early Oligocene. The Badlands fauna of the Chadron Formation reflects an environment that was not a grassland, even though it was also not a closed forest. The Brule fauna begins to show some signals of a more open environment, but the full development of Great Plains grassland ecology appears to post-date the Badlands sequence, occurring primarily in the Miocene, which is not directly represented in the Badlands formations. What the Badlands record shows, then, is not the establishment of the grasslands themselves, but the world that existed immediately before that transformation, the world that would eventually be replaced by the open grasslands of the modern Great Plains. Understanding that earlier world and the processes that transformed it is essential to understanding how the modern Great Plains ecosystem came to be. Climate reconstruction from the Badlands fossil record extends beyond simply noting which species were present. Paleontologists and paleoclimatologists use multiple methods to extract environmental information from the Badlands sediments. The stable isotope chemistry of fossil teeth and bones can provide information about the temperature and hydrology of the environment in which the animal lived. The physical properties of fossil soils, called paleosols, preserved within the formation, can be analyzed to reconstruct past soil moisture, temperature, and atmospheric conditions. The presence or absence of certain plant fossil material, including fossil pollen and plant fragments preserved in the sediment, can contribute to reconstructions of past vegetation. Together, these lines of evidence paint a picture of a landscape that was over the span of the Eocene-Oligocene transition, undergoing a slow but significant environmental transformation, cooling, drying, and opening up, becoming progressively less like the warm, humid, vegetated landscape of the Eocene, and more like the cooler, more seasonal, more open landscape that would eventually characterize the Oligocene and the Miocene Great Plains. The animals of the Badlands were not passive recipients of this change. They responded to it through extinction, through evolutionary change, through shifts in the relative abundance of different groups, in ways that the fossil record has preserved and that modern science is still working to fully understand. This record of biological response to environmental change has a significance that extends beyond the purely historical. In an era when Earth's climate is again undergoing significant change, driven now by human activity rather than by the astronomical and geological forces that drove the Eocene-Oligocene transition, the fossil record of events, like the one documented in the Badlands, provides one of the few empirical datasets we have for understanding how living systems respond to major environmental shifts. The timescales are different, the rates of change are different, the causes are different, but the fundamental question, how do ecosystems respond when the conditions that sustain them begin to change, is one that the Badlands fossil record has been addressing in its quiet and patient way for nearly 2 centuries. There is a portion of the Badlands that most visitors never see. The roads that pass through Badlands National Park provide access to a series of overlooks from which the formations can be viewed across considerable distances. These vantage points are genuinely impressive. The scale of the landscape becomes apparent from them in a way that is difficult to appreciate from the ground level of the formations themselves. But they show the Badlands from the outside, as it were, from the perspective of the surrounding prairie, looking into the formations rather than from within them. Within the formations themselves, the landscape is different, more intimate, and in some ways more complex. The broad visual impression of ridges and spires seen from a distance resolves at ground level into a maze of narrow gullies and dry washes, steeply eroded channels barely wide enough to walk through in single file, and small canyon systems that cut deeply into the formation in directions that are not obvious from the surrounding prairie. These are the hidden canyons, not hidden in any mysterious or secret sense, but simply not visible from the roads, not accessible without leaving the established trails, and rarely visited by anyone except researchers and the occasional careful backcountry traveler. The hidden canyons of the Badlands are products of the same erosional processes that shape the larger formations, simply operating at a smaller scale. Water moving across the surface of the formations does not flow uniformly. It concentrates in low points, follows the path of least resistance downslope, and carves increasingly defined channels as it goes. Over time, a small surface irregularity becomes a shallow drainage, which becomes a deeper gully, which becomes, in the most developed cases, a narrow canyon cutting several meters into the formation. The walls of these small canyons expose cross-sections of the sedimentary sequence that are often extraordinarily detailed. Thin layers that would be invisible in the broader landscape become clearly distinct at this scale, and the transitions between different units of the formation can sometimes be traced with great precision. For paleontologists, these hidden canyon systems are often particularly productive. The concentrated erosion that forms them removes rock efficiently, exposing fossil material that may have been buried deeply below the original surface. The narrow, sheltered nature of the canyons also means that fossils emerging from the walls are somewhat protected from the most severe weathering. They may remain in good condition for longer than fossils exposed on the open slopes of a broad formation face. Survey work in the hidden canyons of the Badlands has, over the years, produced significant specimens that would not have been found by anyone traveling only along the established roads and overlooks. The experience of being inside one of these small canyon systems is qualitatively different from the experience of the broader Badlands landscape. The sky narrows to a strip above, the walls on either side close enough to touch in some places. Display the layering of the formation at eye level. You can run a finger along a band of pale siltstone, follow it as it curves slightly around the bend of the canyon. Observe where it is interrupted by a thin seam of volcanic ash. The sound of the wind, which is constant and present on the open ridges, diminishes within the canyon. The walls provide shelter, and the air inside can be noticeably quieter. In the early morning or late evening, when the sun is low, the light reaches the canyon floor only at an angle, falling in narrow bands that illuminate sections of the wall while leaving the rest in deep shadow. It is in environments like this that the experience of the Badlands shifts from the visually dramatic to the geologically intimate. The formations are no longer a panorama. They are a sequence, a record. A wall of pages that you can read at your own pace, moving through the canyon and following the layers as they lead you deeper into the history of the landscape. The dry washes that connect these canyon systems to the broader drainage of the Badlands also deserve attention. These flat-floored channels, carved into the soft sediment and floored with the fine-grained material that has been washed down from the walls above, are episodically active. During significant rain events, water may move through them rapidly, carrying loose material and occasionally exposing new fossil surfaces. In the dry intervals between these events, they are quiet corridors through the landscape, bordered by low walls of eroded sediment and often marked by the tracks of the animals that use them as travel routes. Pronghorn antelope, which are among the most characteristic large mammals of the modern Badlands, move freely through these wash systems. Burrowing owls nest in the eroded banks. Rattlesnakes find shelter among the loose rocks at the base of the canyon walls. The modern wildlife of the Badlands, though entirely different from the ancient fauna preserved in the formations, represents its own kind of ecological community, adapted to the dry, open, semi-arid conditions of the modern Great Plains in ways that reflect millions of years of evolutionary history. The bison that were reintroduced to Badlands National Park in the 1960s and that now roam parts of the park graze on the mixed grass prairie that borders the formations. The black-footed ferret, one of the most endangered mammals in North America, has been the subject of reintroduction efforts in the Badlands region, associated with the prairie dog colonies that the ferret depends upon as its primary food source. These modern animals move through a landscape that was once, tens of millions of years ago, inhabited by entirely different creatures. The ecological relationships, predator and prey, grazer and grassland, burrower and soil, echo the ancient ones in a general sense, even though the specific participants are entirely different. The land supports life now as it supported life then. The forms of that life have changed profoundly. But the fundamental relationship between the landscape and its inhabitants, the flow of energy from plant to animal, from prey to predator, from living organism to the sediment that will eventually cover its remains, continues. The hidden canyons are a reminder that the Badlands contain more than can be seen at a glance. The landscape rewards patience and attention. The further into it you go, whether physically, by moving through the formations on foot, or intellectually, by following the evidence deeper into the geological record, the more complex and interesting it becomes. There is always another layer, always another canyon beyond the visible one. Always something that the first impression of the landscape did not reveal. The work of paleontology in the Badlands has been ongoing for nearly 2 centuries, and the accumulation of that work has produced an understanding of the White River fauna that is, by the standards of the fossil record, unusually detailed and well-grounded. It is worth pausing to consider what that work has actually established, not as a catalogue of species, but as a body of understanding about the ancient world. The White River fauna, as the fossil assemblage of the Badlands and related formations across the Great Plains, is collectively known, represents one of the best documented terrestrial faunas of the Eocene and Oligocene anywhere in the world. The combination of abundant, well-preserved material and more than a century and a half of systematic research has made it a reference point for interpreting Eocene and Oligocene faunas from other regions, a standard against which less well-known fossil assemblages can be compared. What emerges from this accumulated research is a picture of a fauna that was undergoing significant change over the period represented in the Badlands sediments. The late Eocene fauna, the fauna of the Chadron Formation, was, in many respects, the last expression of an older world. The large brontotheres, the various archaic mammalian groups that had diversified following the extinction of the non-avian dinosaurs, the complex browsing communities adapted to warmer and more vegetated conditions. These represent an Eocene world that was drawing to a close as the climate cooled and conditions changed. The Oligocene fauna of the Brule Formation represents the beginning of something new. The dominance of the Oreodons, the diversification of the rhinoceros group. The continued evolution of the horse family toward larger size and more complex teeth. These trends point forward toward the world of the Miocene and beyond the world that would eventually give rise through further evolution and environmental change to the modern fauna of the Great Plains. Paleontologists have also used the Badlands record to investigate questions about the pace and pattern of evolutionary change. Does evolution proceed gradually and continuously, or does it occur in more rapid bursts interspersed with periods of relative stasis? The question has been debated among evolutionary biologists for decades, and the fossil record, with its inevitable incompleteness, does not provide a perfectly clean answer. But the Badlands record, with its unusually continuous sequence of fossiliferous sediment across the Eocene-Oligocene transition, provides one of the better opportunities available to test these ideas against real data. Studies of specific lineages, particularly the horses and various rodent groups, which are represented by abundant material through the sequence, have contributed important empirical data to this discussion. The methods available to paleontologists working in the Badlands have expanded considerably over the last several decades. Isotopic analysis of fossil material, measuring the relative abundances of different forms of carbon, oxygen, and other elements preserved in fossil teeth and bones, can provide information about the diet of ancient animals, the temperature and aridity of the ancient climate, and the nature of the vegetation in the ancient environment. These methods have been applied extensively to Badlands material, producing results that complement and sometimes refine the interpretations derived from the more traditional approaches of comparative anatomy and stratigraphy. High-resolution computed tomography, CT scanning, has allowed paleontologists to examine the internal structure of fossils without physically cutting or damaging them. The internal structure of bones and teeth can reveal information about growth rates, physiology, and sensory capabilities that cannot be inferred from external anatomy alone. CT scanning of Badlands specimens has contributed to understanding aspects of the biology of White River fauna animals that would have been inaccessible to earlier researchers working only with the external surfaces of specimens. The picture that emerges from all of this work, traditional and modern, observational and analytical, is one of a complex and dynamic ancient world populated by animals that were responding to environmental pressures in ways that were both contingent on their specific evolutionary history and constrained by the ecological realities of the environment they inhabited. The Badlands were not a static place, even in the ancient past. They were a changing landscape, inhabited by a changing community of organisms, recording a changing climate, and the record they left in the sediment is one of the most legible pages in the deep history of the American continent. That record is still being read. New specimens continue to emerge from the formations every year. New analytical methods continue to be applied to existing collections. New questions arise as the scientific understanding of the Eocene and Oligocene develops. The Badlands have not finished telling their story. They have simply been telling it very slowly, in the patient language of stone and time, for longer than any human institution has existed to listen. There is a tension at the heart of the Badlands that no amount of scientific progress can fully resolve. The same force that makes this landscape one of the most productive fossil localities in North America is also the force that threatens to destroy that record entirely. Erosion reveals fossils by removing the rock above them, but erosion does not stop once a fossil has been exposed. It continues, indifferently and without pause, working on the newly exposed surface with the same patient energy it has always applied to everything it touches. A fossil that has survived 30 million years within the protective embrace of the surrounding rock may be destroyed within a single human generation once it reaches the surface, cracked by freeze-thaw cycles, dissolved by acidic rainwater, broken apart by the expansion and contraction of repeated wetting and drying, and ultimately reduced to unrecognizable fragments that wash down the slope and are carried away in the next significant rain event. This creates a situation that is genuinely paradoxical. The Badlands are simultaneously one of the richest sources of ancient vertebrate fossils in North America and one of the most active sites of fossil destruction on the continent. Every year, erosion exposes new material. And every year, previously exposed material that was not found and collected before the weather reached it, is lost. Quantifying this loss is not straightforward. A fossil that has been destroyed leaves no record of its existence. Scientists can observe the rate of surface erosion and make reasonable estimates of the volume of rock being removed annually, but translating that volumetric estimate into a number of fossils lost is difficult because the distribution of fossils within the formation is uneven and not fully mapped. What can be said with confidence is that the exposed fossil record of the Badlands, the material that exists at or near the surface at any given moment, represents a temporary state. It is not a stable archive. It is a dynamic and rapidly changing interface between what has been revealed and what will eventually be lost. This reality has shaped the approach of paleontologists working in the Badlands for generations. The urgency of documenting and collecting exposed fossil material before it is destroyed has been a constant theme in the history of Badlands paleontology, from the rapid collecting programs of the 19th century to the more systematic survey and monitoring approaches of the present day. Badlands National Park conducts ongoing paleontological monitoring programs designed to track known fossil localities and identify new ones, partly with the goal of prioritizing collection or protection of material that is at imminent risk of erosion damage. The legal framework governing fossil collection in the Badlands reflects the complexity of the situation. Within the boundaries of Badlands National Park, vertebrate fossils are protected resources. They may not be collected without a scientific permit, and permitted collection must meet specific documentation standards and result in specimens being deposited in approved repositories. This legal protection exists for good reason. The uncontrolled collection of fossil material from protected landscapes, whether by commercial fossil hunters or by well-intentioned but untrained visitors, has historically resulted in the loss of contextual information that is as scientifically important as the specimens themselves. A fossil removed from the rock without documentation of its precise location, orientation, and stratigraphic context is a fossil that has been partially stripped of its scientific value. Outside the park boundaries, the legal situation regarding fossil collection on public lands managed by the Bureau of Land Management or other federal agencies is different and more complicated, a matter of ongoing discussion and occasional legislative attention. Commercial fossil collecting on these lands has been a source of tension between the scientific community, the fossil trade, and landowners for decades. The discovery of significant specimens on private or federal land outside the park has, in some cases, led to legal disputes over ownership and the appropriate disposition of the material. These disputes are not simply legal technicalities. They reflect genuine disagreements about the nature of the fossil record, whether it is best understood as a natural resource to be managed for the public benefit and scientific knowledge, or as a material commodity subject to the same property relationships as any other resource extracted from the land. The scientific community has generally maintained that the contextual information associated with a fossil, its precise location within the stratigraphic sequence, its relationship to other fossils found nearby, the specific character of the surrounding sediment is irreplaceable, and that its loss represents a genuine diminishment of the scientific record. Commercial collectors have sometimes argued that their activities bring specimens to light that would otherwise be destroyed by erosion, and that some proportion of commercially collected material does eventually find its way into museum collections where it can be studied. The debate is ongoing, and the appropriate resolution is not simple. What is not in dispute is that the geological archive of the Badlands is finite. Every cubic centimeter of rock removed by erosion, whether natural erosion working at the rate of fractions of an inch per year or human activity of any kind, is material that will never be returned. The fossils it contained, whether retrieved by science or destroyed by weather, represent the only record of the organisms that produced them. Once that record is gone, it is gone permanently, and no amount of future scientific progress will be able to reconstruct what was lost. This is the weight that hangs over all work in the Badlands. It is not a paralyzing weight. Science continues, and significant discoveries continue to emerge from the formations every year, but it is a real one. The landscape is an archive with a deadline, and the deadline is written in the language of weather and time. Of all the questions that the Badlands pose, perhaps the most compelling is the simplest: how much remains? Of the fossil record that was laid down in the Chadron and Brule formations during the Eocene and Oligocene, how much still exists within the rock, buried, preserved, waiting to be reached by erosion or by scientific excavation? And of that portion, how much will eventually be recovered before natural erosion destroys it? These are questions to which no precise answer exists. The total volume of fossiliferous sediment in the Badlands formations is large, far larger than the amount that has been studied or collected in nearly 2 centuries of paleontological work. The surface exposures that paleontologists have systematically surveyed represent only a fraction of the total extent of the formation. And the subsurface, the portions of the formation that lie below the current erosion surface and have not yet been reached, extends downward to depths that have been only partially explored through drilling and geological survey work. What we can say, based on the density of fossil material in the portions of the formation that have been studied, is that the Badlands almost certainly contain a very large number of fossils that have not yet been found. The formation is extensive. The depositional environment was, during the relevant periods, consistently favorable to fossilization. The range of animal groups represented in the known fossil record suggests a diverse fauna, and faunal diversity, combined with the length of the time interval represented in the formation, implies a substantial total number of individual organisms that were alive in this region during the Eocene and Oligocene. Some of those organisms undoubtedly left no fossil record at all. Their remains were destroyed before burial, or buried in conditions that did not favor preservation, or buried but subsequently destroyed by chemical processes operating within the rock. This is the normal situation for the vast majority of organisms that have ever lived. But some fraction of the animals that lived in the ancient Badlands environment were preserved, and some fraction of those preserved remains survive within the formation today, and some fraction of those surviving remains will eventually be exposed at the surface and given the opportunity to be found. What species are represented in that buried record? That question cannot be answered without doing the work of excavation and description. The known fauna of the White River Formation is substantial. Dozens of species of mammals, reptiles, birds, and other vertebrates have been documented from the Badlands and related formations. But the known fauna is certainly not complete. New species continue to be described from Badlands material. The discovery in 2010 of the exceptionally well-preserved fossil of a new species of small, horse-like animal, Mesohippus material, that revealed anatomical details not previously known, is one example of how the Badlands record continues to produce genuinely new information even after generations of study. And for every such discovery that reaches scientific publication, there are presumably others still waiting within the rock, in localities that have not yet been reached by erosion or visited by a trained observer. The deeper question, what can we expect to find that we have not yet found, is one that scientists approach with appropriate caution. It is tempting to speculate about dramatic discoveries, about complete skeletons of unknown giants or perfectly preserved specimens of transitional forms that would resolve long-standing scientific debates. Such discoveries do occasionally occur in the Badlands and at other fossil localities around the world, but the routine work of paleontology is less dramatic and more important than these exceptional cases suggest. Every new specimen contributes something, a tooth that refines the known distribution of a species, a partial skeleton that clarifies a disputed anatomical feature, a fossil found in a previously unfossiliferous horizon that extends the known temporal range of a lineage. These small increments of knowledge, accumulated over time and interpreted in the context of the broader record, are how the picture of the ancient world is gradually assembled. There is also the possibility, not a certainty, but a genuine possibility, that some of what remains buried in the Badlands represents groups or species that are not yet known from any other locality. The White River fauna is well studied, but well studied in the context of a fossil record covering millions of years, and a vast geographic area means something different from completely known. The preservation of the fossil record is inherently biased towards certain types of environments, certain body sizes, and certain types of tissues. Animals that were rare, or that lived in habitats not favorable to fossilization, or that had relatively fragile skeletons, are likely to be underrepresented or absent from the known record, even if they were actually present in the ancient ecosystem. Some of what lies beneath the Badlands may represent exactly these kinds of organisms, animals that existed, that played roles in the ancient ecosystem, but whose remains were rarely preserved and have not yet been found. The Badlands also extend, in terms of the same or related formations, far beyond the boundaries of the national park. The White River Group, the collection of geological formations that includes the Chadron and Brule outcrops across a substantial area of the Great Plains, including parts of Nebraska, Wyoming, Colorado, and other states. The Badlands of South Dakota are the most famous and extensively studied portion of this larger geological unit, but they are not the only portion. Research at other outcrops of the White River Group has produced important specimens and contributed to the overall understanding of the fauna, and significant work continues at localities across the region. What lies beneath is not a fixed quantity. It is a dynamic one, being continuously modified by the erosion that removes material from the surface, and in doing so brings deeper material closer to the point of exposure. Every year that passes, the hidden record of the Badlands becomes slightly less hidden. Some of what was buried last year is now closer to the surface than it was. Some of what was at the surface last year has been carried away by rain and wind and is gone. The boundary between the known and the unknown moves slowly and continuously through the rock. The Badlands will continue to change. This is not a prediction. It is a statement of geological continuity, an acknowledgement that the processes that have been shaping this landscape for hundreds of thousands of years have not stopped and show no sign of stopping. The same rain that falls on the formations today is doing the same work that rain has always done here. The same wind that moves across the ridges in the early morning is carrying away the same fine particles of sediment that it has always carried. The formations are lower today than they were 1,000 years ago. They will be lower still 1,000 years from now. The landscape is in motion, and it will remain in motion for as long as the forces of weather and gravity continue to operate on the exposed surface of the sediment. What will the Badlands look like in 10,000 years? The question is genuinely interesting, even if the answer is necessarily speculative. At current rates of erosion, which vary considerably depending on local conditions and are not uniform across the landscape, the formations will be substantially reduced from their current extent. Some of the ridges and spires that are prominent features of the modern landscape will have been worn down significantly. Some of the deeper portions of the formation, currently buried well below the surface, will have been exposed. The canyon systems that are now relatively shallow will have deepened and widened. The landscape will retain its fundamental character, soft sedimentary rock being slowly reduced by water and wind, but its specific topography will have changed in ways that would be apparent to anyone familiar with the modern landscape. The climate of the Great Plains may also change over those timescales, and changes in climate will affect the rate and character of erosion. If rainfall patterns shift, as they have shifted many times over the history of the Great Plains, the rate at which water moves across the formations will change. If vegetation patterns shift, the amount of bare ground exposed to raindrop impact and surface runoff will change. These interactions between climate, vegetation, and erosion are complex and not easily predicted, but they are real, and they have shaped the history of the Badlands landscape throughout the period of its formation. The scientific and cultural importance of the Badlands landscape is unlikely to diminish as the landscape changes. If anything, the recognition of what is at stake, the irreplaceable nature of the fossil record, the extraordinary geological history preserved in the formations, the cultural significance of the landscape to the Lakota and to American natural history more broadly, has grown considerably over the last several decades. Badlands National Park was designated a World Heritage Site in 1978. Though it has since been delisted, the recognition reflected a global understanding of the landscape's significance. The ongoing scientific research conducted in the park and in the surrounding region represents a commitment to understanding the record, while the opportunity to do so remains. The Oglala Lakota, whose Pine Ridge Reservation borders and partially overlaps the southern unit of Badlands National Park, an area sometimes called the Stronghold Unit, maintain a particular and historically significant relationship with this landscape. The Stronghold Unit includes the site of the last major ghost dance gathering of 1890, a moment of profound significance in the history of Lakota, resistance to the dispossession of their lands and the suppression of their cultural practices. The landscape that contains this history is the same landscape that contains the Eocene and Oligocene fossil record, a reminder that the Badlands carry multiple layers of historical significance, human and geological, and that the scientific story of the ancient world preserved in the formations exists alongside, and is not more important than the human stories of the people who have called this landscape home. The co-management of the Badlands landscape, the ongoing negotiation between the National Park Service, the Oglala Sioux tribe, and other stakeholders over how the Badlands are managed, interpreted, and protected reflects a contemporary understanding that landscapes of this significance carry multiple kinds of value and multiple kinds of responsibility. The geological and paleontological record is one layer of that significance. The cultural and historical record is another. And the living landscape, the prairie ecosystem, the wildlife, the ongoing processes of erosion and deposition, is a third. All of these layers exist simultaneously in the Badlands. They overlap, interact, and sometimes create tensions that require careful thought and respectful negotiation to address. The management of a landscape this complex is itself a kind of science, an ongoing process of learning, adjusting, and acknowledging the limits of any single perspective. The future of the Badlands, in the broadest sense, is the future of all these layers together. It is worth spending a moment with the idea of what we do not know. In the history of Badlands paleontology, there have been moments when a new discovery overturned or significantly revised an established interpretation. A specimen found in an unexpected stratigraphic position extended the known range of a species or group in ways that required rethinking the pattern of faunal change across the Eocene-Oligocene boundary. A well-preserved skeleton revealed anatomical details that changed the understanding of how a particular animal moved or fed. A new locality, surveyed for the first time, produced material from a horizon previously thought to be unfossiliferous. These moments of revision are not failures of previous science. They are the normal functioning of a scientific process that operates with incomplete information and that corrects itself as new information becomes available. The history of Badlands paleontology is, in this sense, a history of progressive refinement, of a picture that has become increasingly detailed and accurate over time, without ever reaching a state of complete knowledge. Complete knowledge of the ancient Badlands ecosystem is not an attainable goal. The fossil record is too incomplete, the preservational biases too systematic, and the complexity of the original ecosystem too great for any finite amount of research to fully reconstruct what once existed here. This is not a limitation unique to the Badlands. It is a fundamental feature of paleontology as a discipline that works by its nature, with evidence that is fragmentary, biased, and separated from its original context by geological processes that distort and obscure as much as they preserve. What the discipline has nonetheless managed to reconstruct, from the fragmentary, biased, distorted evidence of the Badlands fossil record, is genuinely remarkable. We know, with reasonable confidence, the broad outlines of the late Eocene and Oligocene fauna of this region. We know which major groups were present, roughly when they appeared and disappeared, and something about how they lived. We know the general character of the ancient environment, that it was warmer and wetter than the modern Badlands, that it was dominated by river systems and their associated floodplains, that it transitioned over time toward cooler and drier conditions. We know that the landscape was undergoing a significant biological transition at the Eocene-Oligocene boundary, and we know something about how different animal groups responded to that transition. What we do not know, what the buried record may someday tell us, or may take to its grave in the ongoing erosion of the formations, includes the fine details, the specific composition of the ancient plant communities, the behavior of the animals whose bones we have found, the ecological relationships between species that coexisted but left few traces of their interactions in the rock, the fate of individual lineages during the Eocene-Oligocene transition, the full diversity of small, fragile, or rare organisms that lived in the ancient Badlands but left little or nothing in the fossil record. Some of these unknowns may eventually be resolved by future research. New analytical methods may extract information from existing specimens that earlier techniques could not access. New localities, found through systematic survey or exposed by erosion, may produce material that fills gaps in the current record. New theoretical frameworks may allow scientists to interpret existing evidence in ways that reveal patterns previously invisible. Some of the unknowns will never be resolved. The evidence has already been destroyed by the same erosion that created the exposures in the first place, working on material that was exposed before anyone thought to look for it, or by the natural processes of decomposition and diagenesis that prevented preservation in the first place. The ancient Badlands ecosystem was vastly more complex than anything the fossil record can fully represent, and some portion of that complexity is simply and permanently inaccessible. Living with that permanent incompleteness is part of what it means to study the deep past. The fossil record does not offer certainty. It offers evidence, partial, suggestive, sometimes revelatory, but never complete. Learning to read that evidence carefully, to distinguish what it actually demonstrates from what it merely suggests, and to acknowledge openly and honestly the limits of what can be known. This is the intellectual discipline that the best paleontology demands. It is also, in a broader sense, an important model for how to engage with any body of incomplete evidence about a complex past. The Badlands reward that kind of careful engagement. They do not yield their secrets to impatience or to the desire for simple answers. But to the observer who is willing to look slowly and to think carefully, they offer something extraordinary, a window into a world that existed millions of years before any human being walked the continent, preserved in the soft walls of an eroded landscape, waiting to be understood. We have been traveling backward through time. We began at the surface, in the early morning light, with the wind moving across the ridges and the canyon walls just beginning to catch the first light of the day. We moved downward through the geological sequence, from the modern landscape into the rock, from the rock into the ancient sediment, from the sediment into the environments that produced it, from the environments into the lives of the animals that inhabited them. We watched the landscape change around us, growing warmer, wetter, more vegetated, more populated with creatures that no longer exist. We watched it change again, cooling, drying, shifting, and we observed the responses of the living community to those changes, written in the fossil record with a patience that no human archive can match. Now we begin the return journey, slowly, without urgency. The ancient world that the Badlands preserve is not accessible to us in the way that a historical document or an archaeological site is accessible. We cannot visit it. We cannot hear its sounds or breathe its air or watch its animals move. We can only reconstruct it. Carefully and imperfectly from the evidence preserved in the rock, evidence that is incomplete by nature, biased by the accident of preservation, and separated from the original world, it represents by a gulf of time so vast that it is almost impossible to meaningfully comprehend. And yet the reconstruction is not nothing. The bones we have found, the teeth we have analyzed, the sediments we have dated and interpreted, the isotopic signals we have extracted from mineralized enamel. All of these have allowed science to build a picture of the ancient Badlands that is, in its broad outlines, trustworthy and meaningful. We know that this landscape was once very different. We know something about what it looked like and something about what lived in it. We know that it changed, and we know something about why. And we know that the evidence of all of this, incomplete as it is still emerging from the walls of the formations, year by year, layer by layer, one fragment at a time. There is something deeply affecting about this, if you allow yourself to sit with it. The Brontothea that left its bones in the Chadron Formation died in a world that was entirely unfamiliar. A warm, river-crossed plain under a sky that looked broadly like our sky, but that looked down on a landscape utterly unlike anything that exists today on this continent. The animal that died there had no awareness that it was dying in a place that would one day be significant to science. It had no awareness that its bones would be slowly mineralized, buried under accumulating sediment, and eventually, after 35 million years, eroded back to the surface of a changed and unrecognizable world to be found by creatures so different from anything that existed in its own time that no comparison would have been meaningful. It simply lived and died and was buried and remained. And the remaining is the miracle. Not a supernatural miracle, a natural one. The ordinary miracle of preservation of the right conditions occurring at the right time of sediment falling over bone before the bone could be scattered of groundwater moving through rock in ways that replaced organic material with mineral. Of geological forces working slowly and without intention to bring what was buried back toward the surface. The miracle that the Badlands are not simply what they appear to be, not simply a dry, eroded, semi-arid landscape at the edge of the modern Great Plains, but something far older, far stranger, and far more full of history than their quiet appearance suggests. The wind has not stopped. It moves across the ridges in the same direction it has always moved, from the west, predominantly, bending the dry grass at the edge of the formations and carrying fine particles of sediment away from the exposed surfaces of the canyon walls. It has been doing this for a very long time, not always at the same rate, not always from exactly the same direction, and not without interruption by the weather systems that move through the Great Plains with seasonal regularity. But continuously, in the sense that matters geologically, continuously enough that its cumulative effect, compounded over thousands of years, amounts to the removal of enormous quantities of material from the landscape. The rain has not stopped either. It falls on the formations with irregular frequency, more in the spring and early summer, less in the dry heat of late summer. Sometimes in violent convective storms that send sheets of water across the nearly bare surface of the formations and carve new channels in the soft sediment within hours. Each rain event carries away some quantity of material. Each season brings a cycle of wetting and drying that stresses the exposed rock surface and contributes to its ongoing fragmentation. Each winter brings freeze-thaw cycles that work on the water trapped in cracks and pores within the rock, expanding as ice and contracting as water, gradually widening the fractures that allow erosion to work more deeply into the formation. These forces are not hurrying. They have never hurried. They operate on a timescale for which human language does not have entirely satisfying words. Not slow in the way that a slow process feels slow to a waiting observer, but slow in the sense that the relevant unit of time is not a year or a decade, or a century, but a span of time so long that the entire recorded history of human civilization fits within it many times over without filling it. And within those forces, and within that time, and within the soft walls of the formations that the forces are so patiently dismantling, the fossils continue their own patient waiting. Bones that were buried in river mud 30 million years ago are, at this moment, perhaps an inch from the surface, or a foot, or 10 feet, or 100. Some of them will reach the surface within a human lifetime. Some will not be exposed for thousands of years. Some will be destroyed by the same erosion that eventually brings them to the surface, crumbling as they emerge rather than being preserved in recognizable form. And some will be found, carefully excavated, documented, transporting, prepared, studied, and added to the scientific record, adding their small but irreplaceable contribution to the growing picture of the ancient world. The landscape does not know about any of this. It does not curate its fossil record. It does not prioritize the preservation of significant specimens over insignificant ones. It does not hurry to expose material that science would find important, and it does not pause to allow adequate time for material that has just been exposed to be found before the next rain erodes it further. It simply continues, as it has always continued, doing what landscapes do, changing, slowly, in response to the forces that act upon it. It is only from the human side of this encounter that the urgency arises. The landscape has no stake in whether its fossils are found or lost. We do, or rather we have decided that we do, that the ancient record preserved in these formations is worth understanding. That the lives of the animals who died here tens of millions of years ago deserve to be known, that the story of how this landscape and its inhabitants changed over deep time is a story worth telling and worth hearing. That decision, the decision to find the fossils, to study them, to reconstruct the ancient world they represent, and to understand what that reconstruction can tell us about the deeper history of life on this continent, is one of the more remarkable things that the human species has chosen to do with its brief tenure on Earth. It requires patience and careful observation and the willingness to work with incomplete evidence and acknowledge the limits of what can be known. It requires a particular kind of humility before the scale of deep time, an acceptance that human existence is a very small part of a very large story, and that the value of understanding the larger story does not depend on human beings playing the central role in it. The Badlands offer that understanding in their quiet, unhurried way to anyone willing to accept it. The sun is moving toward the western horizon now. The light is changing again, becoming warmer, more golden, falling across the formations at an angle that deepens the shadow in every notch and gully and makes the horizontal banding of the layers more distinct than it is at midday. The formations glow in this light. They have always done so, at this hour, in this season, with this particular quality of late afternoon illumination. They will continue to do so long after the last human being who has ever looked at them is gone. The wind continues in the lower reaches of the formations, where the dry washes flatten out into the broader drainage of the surrounding prairie. A small herd of pronghorn antelope is moving slowly eastward, grazing, pausing, moving again in the unhurried rhythm of large herbivores in an environment that offers enough food to sustain them without requiring urgency. They move through the same landscape that 35 million years ago was inhabited by animals that played some of the same ecological roles. Browsers and grazers moving through a river-crossed plain in herds following the seasonal availability of vegetation, leaving their own tracks in the soft ground near the water. The pronghorn do not know that the cliffs they pass beside contain the bones of animals that were here before them. They do not need to know. They are simply living in the present of a landscape with an extraordinarily deep past. Somewhere in the walls of the canyon above the dry wash, at a depth that the current surface of the formation has not yet reached, there may be a bone. It may be a tooth. It may be a fragment of skull, or a piece of a limb bone, or the delicate arc of a rib. It has been there, within the rock, for 30 million years or more. In 10 years, or 100, or 1,000, depending on the precise rate of erosion at that location, and on the exact depth at which the fossil lies, it may reach the surface, or it may not. The arithmetic of erosion and preservation is not predictable at the level of individual specimens, but the probability that something is there, that somewhere within the formations currently visible within the vast buried extent of the White River Group across the Great Plains. There are fossils that have not yet been found representing animals or moments in geological history that are not yet known to science. That probability is very high. The known record of the ancient Badlands is substantial. The unknown record is almost certainly larger still. What will be found, and when, and by whom, and what it will tell us, these are questions that belong to the future. They will be answered not by speculation, but by the patient, systematic work of researchers who will walk across these formations in years and decades to come, scanning the surface of the rock with the careful attention that this kind of work requires watching for the shape or color or texture that is slightly wrong for the surrounding sediment. That belongs to a different world that is asking after a very long silence to be found. There is a particular way of thinking about a landscape like the Badlands that takes some time to arrive at, but that, once arrived at, changes the way the landscape appears. At first, the Badlands look like a place where something has been worn away. The ridges and spires and canyon walls look like remnants, the last standing portions of something that was once more complete, now being steadily reduced toward nothing. And in a narrow sense, this is accurate. The formations are being eroded. They are smaller now than they were 1,000 years ago, and they will be smaller still 1,000 years from now. Eventually, over timescales much longer than those represented in the fossil record itself, the formations will be gone entirely, reduced to sediment that will be carried by rivers to lower ground, deposited in new basins, and potentially, over geological time, buried and lithified into new rock. The Badlands are a temporary feature of the Earth's surface, as all features of the Earth's surface are temporary on geological timescales. But there is another way to see it. The formations are not only remnants of what has been lost. They are also the containers of what has been kept. Within every remaining cubic meter of Badlands sediment, there is a preserved record, imperfect, incomplete, but genuine, of what existed here during the Eocene and Oligocene. Every layer of rock that has not yet been eroded is still holding something. The landscape is not simply being worn away toward nothing. It is being slowly read. The erosion is not destruction of meaning. It is, as much as anything, revelation. The bones that emerge from the formations do not belong to dead animals in the simple sense. They are evidence of lives that were fully lived, in an environment that was fully real at a time that was, for the animals that existed within it, the present. Those animals did not know they were living in the Eocene. They did not know that the world they inhabited would eventually be buried and compressed into rock, or that the rock would eventually be exposed by erosion, or that creatures inconceivably different from themselves would one day find their bones and spend considerable effort trying to understand them. They simply lived. They fed and moved and interacted with their environment and eventually died as all living things die. The landscape of the Badlands holds the memory of those lives, not a perfect memory, not a complete one, but a real one. A memory made of stone and mineral and the slow chemistry of deep time. A memory that requires patience and science and careful attention to read, but that is, for those willing to make that effort, genuinely legible. And that legibility is one of the most extraordinary things about the natural world. Let us return now to where we began. The light is nearly gone from the sky above the Badlands. The last warmth of the sun has faded from the tops of the formations, and the canyon below is now entirely in shadow. The wind has quieted slightly, as it often does in the evening hours on the Great Plains, though it has not stopped entirely. A soft, steady movement of air across the grass at the edge of the formations, bending the stems gently in one direction and then releasing them. The landscape in the fading light looks older than it does at midday. The formations lose their color as the light fails, becoming shades of gray and dark tan, their individual layers less distinct, their overall silhouette simply a series of irregular shapes rising against a sky that is still faintly bright in the west. In this light, the Badlands look exactly like what they are, a very old landscape, worn down from something larger, carrying within it a record that no surface appearance can fully convey. Somewhere in the walls of those formations, at various depths and various distances from the current surface, are the fossils that have not yet been found. Some of them are within inches of the surface, perhaps close enough that the next significant rain will bring them into contact with the open air for the first time in 30 million years. Others are deeper and will require decades or centuries of erosion before they approach the surface. Others will never reach the surface because the erosion will destroy them before fully exposing them, or because they lie in portions of the formation that are buried far below the current level of the landscape and will not be reached by erosion within any humanly meaningful time frame. The ancient world that produced them, the warm, river-crossed plain of the Eocene and the somewhat cooler, more open landscape of the Oligocene, is gone as completely as any world can be gone. Its plants have not left living descendants on this landscape. Its specific arrangement of rivers and floodplains has been entirely rearranged by millions of years of geological change. The sky above it was lit by the same sun that lights the modern Badlands, but the atmosphere through which the light traveled was not quite the same, and the world it illuminated was wholly different. And yet the memory of that world is here. It is here in the grey and buff and tan of the formations. It is here in the thin white lines of volcanic ash that cross the canyon walls at irregular intervals. It is here in the texture of the exposed mudstone, a texture that reflects the texture of ancient river mud. Laid down quietly on an Oligocene floodplain, while the animals of that world moved through the shallow water nearby, and the sky above was entirely free of any trace of what would eventually become human civilization. It is here in the bones. Human civilization, all of it, from the earliest cities of the ancient world to the present day, occupies a span of roughly 10,000 years. Modern human beings, as a species, have existed for perhaps 300,000 years. The fossil-bearing sediments of the Badlands began accumulating more than 30 million years ago. The gap between the ancient world preserved in these formations and the modern world in which we study them is so large that it resists genuine comprehension. We can state it in numbers. We can illustrate it with analogies, but we cannot truly feel it in the way that we feel the passage of a human lifetime. What we can feel, or rather, what we can slowly cultivate through patient attention to landscapes like the Badlands, is a sense of the depth of the past. A sense that the world we inhabit is not the world that has always existed, and that the world before ours was not less real for being different. A sense that time, extended to geological scales, reveals processes and patterns that are genuinely different from anything human history encompasses, and that understanding those processes and patterns changes, in some quiet but significant way, how we understand our own moment within the larger story. The Badlands offer that change of perspective to anyone willing to receive it, not dramatically, not insistently, quietly, the way all deep geological things offer themselves at the pace of erosion, which is patient beyond anything that human language was designed to describe. The wind moves across the ridges. The last light fades from the western sky, and beneath the pale walls of the formations, in the cool dark of the sediment that has not yet been reached by the weather, the ancient record continues its long, unhurried wait. It has waited 30 million years already. It can wait a little longer. End of documentary. Thank you for listening to History's Sleepy Time. If this quiet journey through deep time was something you valued, please consider subscribing, leaving a kind comment, or sharing the channel with someone who might enjoy it. It means a great deal, and it helps us keep making these long, calm documentaries together. Sleep well.